Welcome back to the course Rocket Propulsion offered by EDAL Systems. In today's class, we will start with fundamentals of rocket propulsion. So first we will see the contents for this topic. So first we will see a detailed history and background about the rocket propulsion. Then we will cover the applications of rocket propulsion. Then it will be classification of rocket engines. So a complete classification will be given. Then some important definitions which are very useful when you are studying rocket propulsion. Then second last we have selection of rocket propulsion systems. So which rocket propulsion system is an appropriate for your problem definition? So we will see the selection criteria. Then rocket testing. So what all kind of rocket testings are available and how the tests are carried out, what all things are taken care of while carrying out the test. So these all things we will cover up in this topic today. So let's start with history and background. So the history for rocket propulsion goes back into 18th and 19th centuries, where the Chinese developed and used solid propellant in rocket missiles over 800 years ago, and military bombardment rockets were used frequently in the 18th and 19th centuries. So Chinese were the first people to use and to discover about this rocket propulsion, where they used it for military purposes. Then there was a significant development of rocket propulsion in 20th century. So the early pioneers included the Russian Konstantin E. Zolowski, who is credited with the fundamental rocket flight equation and his 1903 proposals to build rocket vehicles. So this person from Russia, he was credited with the fundamental rocket flight equation, and then he proposed to build rocket vehicles. So to use this rocket propulsion systems as rocket vehicles was proposed by this Russian. Then it goes to the German, where the German Hermann Oberth developed a more detailed mathematical theory where he proposed multi-stage vehicles for space flight and fuel-cooled thrust chambers. So after Russian, the Germans also entered, and this person has proposed the multi-stage vehicle for space flight and fuel-cooled thrust chambers, which are even used today. Then the American Robert H. Goddard is credited with the first flight using a liquid propellant rocket engine in 1926. So we can see how this development has been done in rocket propulsions from 18th and 19th century till date, and still we can see there are various developments happen decade by decade in this rocket propulsion industry. But these were the main pioneers who encouraged rocket propulsion and gave the world the idea of how to use a rocket propulsion in their country for respective uses. Then we will see background of rocket propulsion. So what is propulsion? So propulsion mechanism provides a force that moves body that are initially at rest, which changes the velocity that overcomes retarding forces when a body is propelled through a medium. Propulsion is basically a mechanism which will help to provide a force which will help to move a body which is initially at rest position. Then jet propulsion is a means of locomotion whereby a reaction force is imparted to a device by the momentum of an ejected matter. Rocket propulsion is a class of jet propulsion that produces thrust by ejecting matter stored in a flying vehicle called the propellant. So rocket propulsion comes under the class of jet propulsion, in which a thrust is produced by ejecting matter stored in a flying vehicle called the propellant. The propellant is already stored in the flying vehicle, and just it has to get burned such that the thrust force is created and the vehicle moves in a particular direction. So the operating principle for a rocket is Newton's third law of motion, which we all are familiar with, that is, for every action there is an equal and opposite reaction. So if we see this for a rocket propulsion system, then it is very simple that when the propellant is burned, the exhaust gases, they move in downward direction, which will cause the engine to move in forward direction. So this is the basic application of Newton's third law. So in the figure below explains the Newton's third law of motion, that the action which we are creating, that is we are generating the hot gases, that is we are generating the thrust, and the reaction we are getting is that the rocket is moving in the upward direction. So now let's focus on what is the difference between air breathing engine and a rocket engine. So air breathing engines we generally call aircrafts or air breathing engines because the air which is necessary to run that engine, it doesn't carry that air with it. But for rocket engines which are called as non-air breathing engines, the reason is that The engine has to carry its own oxygen or the own air which will help the fuel to burn with it in the space travel. So this is the major difference why we call it as air breathing engine and non-air breathing engines. So under air breathing engines, all the aircraft engines they come under air breathing, and rocket engines, we know what rocket engines are present around. So the first difference which is listed here is that there is limitation of altitude in air breathing. Then for rocket engines we have there is no limitation of altitude and space travel is possible. So air breathing engines they can't go above 12 kilometers or 13 kilometers above that, because above that altitude there is no air present which will help the engine to burn the fuel. So the next difference is flight speed is always less than the jet velocity for air breathing engines, and for rocket engines the flight speed is not limited and it can be greater than jet velocity also. Then it is efficiency is higher than rocket engines and duration of flight is more for air breathing engines, and for rocket engines it is efficiency is low except at extremely high flight speeds and the duration of flight is low. So next we will move on to applications of rocket propulsion. So here we will see some major applications. Because the rocket can reach a performance unequaled by other prime movers, it has its own field of applications and does not usually compete with other propulsion devices. So as we can see, the performance of a rocket engine cannot be compared with any other prime movers, any other propulsion devices. It has its major space of applications. So one of the applications is space launch vehicle. So space launch vehicle is a rocket propellant vehicle used to carry a payload from Earth's surface to space, usually to Earth orbit or beyond. So the various launches which we see today, with the help of space launch vehicles, we are able to explore the space and the universe around using the rocket propulsion. So the major space launch vehicles of India are PSLV, which we are familiar with, and GSLV. Next application here is the spacecraft. Spacecraft is a vehicle or machine designed to fly in outer space. So the space launch vehicle, they carry the spacecrafts, the satellite and all the setup into space. The spacecraft are used for a variety of purposes including communications, earth observation, meteorology, navigation, space colonization, planetary exploration and transportation of human beings and cargo. The spacecrafts are mainly used for such applications, and rocket propulsion is the prime mover which is used to launch the spacecraft using space launch vehicles. So some of the spacecrafts of India are the famous Aryabhatta, then Chandrayana, Kalpana, etc. Then the next applications here we will see the missiles. So missile we all know that it is a rocket propellant weapon designed to deliver an explosion warhead with great accuracy at a high speed. So missile vary from small tactical weapons that are effective out to only a few hundred feet to much larger strategic weapons that have ranges of several thousands and miles. So these missiles they also use this rocket propellants to propel in a particular direction. So they vary from a small tactical missiles to a large strategic weapons which are used in military wars and etc. So the major missiles of India are Prithvi, Agni, BrahMos, etc. Then rocket propulsion is mainly used in lethal weapons. So we have seen till now that most of the propulsion devices they use rocket propulsion. But here the weapons which we see, the guns, the rifles, etc., they use this propellant. So gunpowder is the main propellant which they use, which is also called as black powder, which we saw earlier in the history that Chinese were the first to discover how to use this gunpowder in military bombardments. The military guns pistol they all include smokeless black powder as gunpowder or a propellant for ammunition in guns. Then the next application here we will see is long range artillery. So an artillery is a class of heavy military ranged weapons built to launch munitions far beyond the range and power of infantry firearms. So this is the long range artillery which is used mainly for military purposes, and Dhanush is the first long range artillery gun to be produced in India and has been built as a success of the government's Make in India initiative. So these are the various applications of rocket propulsion, in which mostly the rocket propulsion is the main factor without which these all things are not possible. So moving on to the next topic, that is classification of rocket engines, we will see a detailed classification of rocket propulsion. So the first you can see that rocket propulsion can be divided into two parts, that is thermal and non-thermal. So first we will see thermal. Under thermal we have chemical and non-chemical rocket propulsion. propulsion. So again, the chemical rocket propulsion can be divided into bipropellants and monopropellants. So bipropellants is a category where two different kinds of propellants are used. That is, for fuel, the propellant will be different. For oxidizer, the propellant will be different. And monopropellants is the class of chemical rocket propulsion in which a single propellant will have the properties of fuel as well as oxidizer. So the bipropellants can again be classified as solid, liquid, and hybrid. So based on their physical state, they can be classified into solid, liquid, and hybrid. So solid propellants will be the fuel and oxidizer will be present in solid form, whereas in liquid both will be present in liquid forms. In hybrid, it will be a combination of both solid and liquid. Either the fuel will be in solid form or the liquid will be in the solid form, and vice versa. So again, this liquid and hybrid can be classified as pressure fed or pump fed. So how the liquid propellant is fed to the thrust chamber, so based on that it can be classified as pressure fed or pump fed. Moving on to the next category, we will see what are non-thermal rocket propulsion options. So the non-chemical and non-thermal, they both have the same kind of options. So the options are nuclear, beamed, cold gas, solar, electrical, and advanced. So under electrical, we will see four major types, that is electrodynamic, electromagnetic, electrothermal, and electrostatic. So without using any chemicals, the electric charge will be used. Then again under electrothermal, we have two options, that is resistojet and arc jet. Also under electrostatic, we have ion and colloid. So based on the applications, what application we need, either a low thrust rocket engine or high thrust rocket engine, we can select any of the type which we want based on our problem definition. But these are the various options one can explore for the solution. Then again under advanced, there are two categories, that is combining the solar energy and the thermal energy and producing the thrust. And it is the laser. We will discuss each of them briefly in upcoming slides. So the first one we will discuss is chemical rocket engine. So the word itself says that chemical rocket engines means that the chemicals are involved, and based on the chemistry, somehow these reactions are produced and thrust is generated. So we will see how these reactions are produced and how the thrust can be generated using these chemicals. So in chemical rockets, the energy from a high pressure combustion reaction of propellant chemicals, usually a fuel and oxidizing chemical, permits the heating of reaction product gases to very high temperatures. This temperature goes to around 2500 to 4100 degrees Celsius. Then this gas is subsequently expanded in a nozzle and accelerated to high velocities. So again, this jet velocities or the exhaust velocities of rockets, they reach up to 1800 to 4300 meter per second. So these high velocities are needed to be generated such that the rocket escapes the Earth's gravity and move into the space. So this is how the chemical propellants are used to create a high pressure combustion reaction. Then this reaction will generate the products which will be then expanded using a nozzle and accelerated to high velocity. So then according to the physical state of the propellants, that is the fuel and oxidizer, there are several different classes of chemical rocket propulsion devices. So the major ones are solid, liquid, gaseous, and hybrid. So based on how a fuel and the oxidizer are present in their physical state, we can classify chemical rockets into solid rocket propellant, liquid rocket propellant, gaseous, and hybrid rocket propellants. Moving on to the next slide, we will see first the liquid propellant rocket engine. So the name says that they use liquid propellants that are fed under pressure from tanks into the thrust chamber. The liquid bipropellant consists of a liquid oxidizer, for example liquid oxygen, and a liquid fuel, for example kerosene. So both of the fuel and oxidizer are present into liquid state, and then they are fed under pressure from tanks to thrust chambers. So these fuel and oxidizer are stored into tanks, which we can see from the figure on the right, that there is a separate tank for fuel and there is a separate tank for oxidizer. For a combustion reaction, they are taken through pipes under pressure and then they are allowed to enter into the thrust chamber, where they will produce a high pressure combustion reaction. Then a monopropellant, which we discussed earlier, is a single liquid that contains both oxidizing and fuel species. So how it will be ignited is that it decomposes into hot gas when properly catalyzed. So when we are using a monopropellant, we just have to catalyze it properly such that it starts to decompose and produce the thrust. So earlier in the classification, we saw that liquid propellant engines can be again classified in as pressure fed or pump fed. So how these two vary we will see. So the pump-fed liquid rocket systems are used typically in applications with large amount of propellants and high thrusts, such as in space launch vehicles. So space launch vehicle is an application of rocket propulsion in where we saw that we need large amount of propellants and higher thrust. So the thrust which has to be generated in a space launch vehicle, it has to be very much high, and the propellant requirement for such application is also more. So in such kind of applications, a pump-fed liquid propellant systems will be used. So for gas pressure-fed systems, where they are mostly used on low-thrust systems, such as those used for attitude control of flying vehicles. So when a spacecraft has reached to its altitude and is moving in an orbit, so at that time the thrust requirements are not much high. So in those applications, this gas pressure fed systems can be used. Now we will see the advantages and disadvantages of liquid propellant rocket engines. So advantages here are mentioned that higher specific impulse can be attained. We will see what is the specific impulse. Then can be randomly throttled and randomly stopped and restarted. So in the burning time of a liquid propellant rocket engines, we can randomly throttle it, we can randomly stop it, or we can restart it again. It can be designed for reuse after field services and checkout. Then thrust chamber or some part of the vehicle can be cooled by propellant and made light, very good advantage when we are carrying such heavy payloads into the space. Then most propellants have non-toxic exhaust which is environmentally acceptable. Otherwise, if we are decomposing a gas or a chemical into an atmosphere, then it will be very harmful and won't be acceptable. So with multiple engines, it can operate with one or more shutoff, so which gives us engine out capability. So if the configuration consists multiple engines and if it faces engine out, then the other spare engine can be used in that place. These are the advantages which we are seeing. Then we'll see some of the disadvantages of liquid propellant rocket engines. The first one is that relatively complex design, more parts or components, then more things to go wrong. So we have seen there are two different tanks involved, then the various walls are present, then pressure has to be maintained. Many things are involved, many components are involved. So any if one thing goes wrong, then more of the things has the proportionality to go wrong. Then spills or leaks of several propellants can be hazardous, corrosive, toxic, and causes fire. So even small leak of any propellant can cause hazardous situation and also can cause fire. Then the tanks need to be pressurized by a separate pressurization system. So the fuel and oxidizer tanks, they need a separate pressurization system to control the pressure. Then sloshing in tank can cause a flight stability problem, but it can be minimized with baffles. So the fuel and oxidizer are present in liquid forms, and due to the motion of the vehicle, sloshing may happen into the tanks, which can cause flight stability problem, which can again be tackled using baffles. So different configuration of baffles can be placed and this problem can be reduced. In the liquid propellant rocket usually requires more volume due to lower average propellant density and the relatively inefficient packaging of engine components. So these are the advantages and disadvantages for liquid rocket propulsion engines. Next we will see is solid rocket motors. So one thing we have to notice here is that liquid propellant rockets are called as liquid propellant rocket engines, while as solid propellant rockets are called as solid propellant rocket motors. So this nomenclature has been decided at very first and it has been used this way till today. So in solid propellant rocket motors, the propellant to be burned is contained within the combustion chamber or the case. Then the solid propellant charge is called the grain and it contains all the chemical elements for complete burning. So the propellant which we're going to use, that is the solid fuel and solid oxidizer, it will be placed inside the combustion chamber itself and it won't need any extra space or tanks to be stored because once you ignite a solid propellant motor, it will completely burn. So once ignited, it usually burns smoothly at a predetermined rate on all the exposed internal surfaces of the grain. So grain is the solid propellant charge which is placed inside the combustion chamber and there are various grain configurations also. So we can see in the figure to the right that how this fuel and oxidizer are present in solid form and they are placed as propellant grain inside the combustion chamber and an igniter is placed in between such that when it is ignited, the complete grain will burn continuously and then the exhaust gases will be expanded through a nozzle. at the end. So once ignited, the motor combustion proceeds in an orderly manner until essentially all propellant has been consumed. As the whole grain consists of the solid and fuel combined together, so once it is ignited, it is very difficult to stop in between. And there are no feed systems or valves, and thus it makes it a simple and unique design. As we can see, the geometry is simple. You just have to place your propellant grain inside the chamber, and then you have to ignite. So no valves are present, no pressurization is present, no feed systems are there. Thus it makes the design very simple and very useful for rocket propulsion applications. Now we will see some of the advantages and disadvantages of solid rocket motors. So the first one, that is advantages, that you have seen, it is very simple, few or no moving parts, and it is very easy to operate. It just have little pre-flight checkout. Then it is ready to operate quickly. It will not leak, it will not spill or slosh. This is the very good advantage we can see for solid propellant rocket motors compared to liquid propellant rocket engines. So sometimes less overall weight for low total impulse application. So even this can be used for low total impulse application. Then can be stored for 10 to 30 years. We can use it even if it's stored for 10 to 30 years. Usually it has higher overall density, allows more compact package, smaller vehicle, which will give us less drag. Then can be designed for a recovery, refurbishing, and reuse, which are termed as space shuttle solid rocket motors. Then thrust termination devices permit control over total impulse. So these are the advantages for solid propellant rocket motors, and now we will see some of the disadvantages, that many require environmental permit and safety features for transport on public conveyances. So there are some environmental threats when we use a solid propellant rocket motor. So as we have seen, as once ignited, the rocket motor will burn continuously until the propellant is consumed. So it is very difficult to transport this propellant from one space to another space. Then explosion and fire potential is larger. Failure can be catastrophic. Most cannot accept bullet impact or being dropped onto a hard surface. Then it requires an ignition system. That is the disadvantage over the liquid propellant rocket engines, because they don't need an igniter. Then exhaust gases are usually toxic for composite propellants containing ammonium perchlorate. Then only some motors can be stopped at random, but motor becomes disabled. So there are some propellants which are used for this solid propellant motors which can be stopped at between, but then again this motor will become disabled and it cannot be used again. So that will be a waste. And the major disadvantage, that is once ignited, it cannot change predetermined thrust or duration. So these are the features and limitations of solid propellant rocket motors. And now we will see the next category, that is gaseous propellant rocket motors. So in gaseous propellant rocket motors, they use a stored high pressure gas such as air, nitrogen, or helium as their working fluid or propellant. The stored gas requires relatively heavy tanks. So as they have to store this gaseous propellants under high pressure, they need relatively very high tanks. So this kind of gaseous propellant rocket motors were used for low thrust maneuvers and for attitude control systems before, but some are used today also. Since it has to carry very heavy tanks and a very good pressurization system with it, the use of such gaseous rocket propellant motors have reduced. And heating the gas by electrical energy or by combustion of certain monopropellants improves the performance, and this has often been called as warm gas propellant rocket propulsion. Moving on to the next, that is hybrid propellant rocket propulsion systems. So they use both a liquid and a solid propellant. So for example, if we have a liquid oxidizing agent which is injected into a combustion chamber filled with a solid carbonaceous fuel grain, then the chemical reaction produces hot combustion gases, and thus this kind of propulsion system is called as hybrid propellant rocket propulsion system. So we can see the concept is very simple, where the liquid oxidizer is fused with solid fuel and then it is allowed to expand using a nozzle. So this way the hybrid propulsion system works. The next we will see is nuclear rocket engines. So here the source of energy to be used in nuclear rocket engines is the nuclear energy. So two different types of nuclear energy sources have been investigated for delivering heat to a working fluid, usually liquid hydrogen. However, none can be considered fully developed today and none have flown. So mostly in nuclear rockets, liquid hydrogen is used as the working fluid, that is liquid propellant for fuel, and two different kinds of nuclear energy sources have been investigated till today, which we are very much familiar with, that is nuclear fission and nuclear fusion. So they are the fission reactor and the fusion reactor. Both are basically extensions of liquid propellant rocket engines, and the heating of the gas is accomplished by energy derived from transformations within the nuclei of atoms. So in nuclear fission reactor rocket, heat can be generated by the fission of uranium in solid reactor material and subsequently transferred to the working. So this uranium atom will be used to combine with this liquid hydrogen, where it will be decomposed into several molecules and then would be allowed to enter into the solid reactor material, where it will react with the liquid hydrogen. So there were concerns with the endurance of the materials at high temperature and intense radiations, power level control, cooling a reactor after operation, etc. So no further ground tests of this rocket engines have been undertaken. This was the concept developed earlier, and there were many concerns regarding the temperatures and intense radiations generated because of such nuclear energy use for rocket propulsion. So no ground tests of such kind of rocket engines were undertaken then. Then the next one, which is fusion, which is an alternate way to create nuclear energy which can heat a working fluid. So a number of different concepts have been studied to date, but none are feasible or practical. But nowadays, some of the researchers are focused to include such kind of nuclear rocket engines in the propulsion system by tackling each of the concerns which are showed here. Moving on to the next concept, that is electric rocket propulsion engines. So here the main energy source which will create the thrust is the electrical power. So in electric propulsion system, the source of the electric power, which may be nuclear, solar, radiation, receivers or batteries, is physically separate from the mechanism that produces the thrust. So the three types which we saw under electric propulsion are the electrothermal, electrostatic and electromagnetic. So in electrothermal rocket propulsions, propellant is heated electrically, which may be by heated resistors or electric arcs, and the hot gas is then thermodynamically expanded and accelerated to supersonic velocity through an exhaust nozzle. So here the thermal energy and the electric energy both will be used together, first to heat up the propellant, and then the hot gas will be thermodynamically expanded and accelerated to supersonic velocity using an exhaust nozzle. Moving on to the next, that is electrostatic rocket, which is also called as an ion rocket. A working fluid is ionized and then electrically charged heavy ions are accelerated to very high velocities by means of electrostatic fields. So using electrostatic fields, a working fluid typically used is xenon is ionized with help of stripping of electrons, and then these heavily charged heavy ions are accelerated to very high velocities with help of electrostatic fields. So the ions are subsequently electrically neutralized. They are combined with electrons to prevent the of a space charge on the vehicle. Then the electromagnetic or the magnetoplasma rocket, an electric plasma, which is an energized hot gas containing ions, electrons, neutral particles, is accelerated by the interaction between electric currents and magnetic fields and ejected at high velocity. So when the electric currents and magnetic fields they interact with each other, the electrical plasma will get accelerated and it will be ejected at high velocities using the nozzle. So the electrostatic and electromagnetic rocket engines, they both work in vacuum. Till now we have seen the history, the background, the different types of rocket propulsion systems, their applications, advantages, disadvantages for solid liquid propellant engines, the nuclear rocket engines and electric rocket engines. Next we will move on to some of the important definitions which are very useful when we are studying rocket propulsion. So the basic principles of rocket propulsion are essentially those of mechanics, thermodynamics and chemistry. So this rocket propulsion, it is a multidisciplinary subject which includes the mechanics, the thermodynamics and chemistry. So the definitions which will be seen today, so the first one, that is total impulse. The total impulse is the product of thrust times duration over the motor burn time, and it is measured in Newton seconds. So this total impulse measures the total amount of momentum imparted to the rocket by the motor. So total impulse is one of the very much important definition in rocket propulsion study. Then it is the thrust force. So thrust is the force which moves the rocket through the air and through space. So when the high pressure combustion reaction takes place and the exhaust gases get accelerated through the nozzle, a thrust force is generated which helps the rocket to move through the air and move through the space. So this thrust force is generated through the application of Newton's third law of motion, which we have discussed earlier in the first slide. Then the burning time, so the duration in which rocket engine is activated to produce this meaningful thrust. So during a space flight, burn time is commonly marked between the ignition and the engine cutoff. So the time from when the ignition has started and the time at which the engine cutoff has made, that is, there is no more thrust generating, there is no more propellant burning. So the duration from that ignition to this engine cutoff is called as burning time, and it is important to calculate this burn time because it will give you how much propellant will be consumed and how much thrust will be generated with the consumption of amount of propellant. Then the next definitions are the specific impulse mass ratio and impulse to weight ratio. So specific impulse is a measure of how efficiently a reaction mass engine using propellant or a jet engine using fuel creates thrust. Next is the mass ratio. So the ratio of the rocket's wet mass to its dry mass is called as mass ratio. So the wet mass includes vehicle plus contents plus propellant, while as the dry mass it just includes the vehicle plus contents. So no propellant mass is included in the dry mass, and mass ratio is the ratio of wet mass to the dry mass. So in aerospace engineering, mass ratio is considered as a measure of the efficiency of rocket. There are various relations which will define how this mass ratio is considered as an efficiency for a rocket. Then the impulse to weight ratio. So ratio of the total impulse divided by the initial or propellant loaded vehicle weight. So this is the impulse to weight ratio, that is the total impulse divided by the weight. So usually a high value indicates an efficient design because the high value will give you high impulse with less weight. So such configurations are very useful in high thrust devices. Then the next definitions we will see is the thrust to weight ratio and the combustion efficiency. So the thrust to weight ratio is a simple ratio of thrust to weight of a flying object. So again, this ratio is the thrust generated to the weight of the propellant loaded vehicle. Even this ratio has to be high because we need high thrust generation with less propellant loaded weight. So the propellant consumed will be less and the thrust generated is more. Then it comes is combustion efficiency. So the combustion efficiency for chemical rockets is the ratio of the actual and the ideal heat of reaction per unit of propellant and is the measure of the source efficiency for creating energy. So this combustion efficiency is mostly calculated for chemical rocket engines. So this covers the important definitions, and now we will go into selection of rocket propulsion systems. So how will you select which rocket propulsion is better for your problem definition? So this process of determining the most suitable rocket propulsion system depends on the application, the ability to express many of the characteristics of propulsion systems quantitatively, the amount of applicable data that are available, the experience of those responsible for making the selection, and the available time and resources to examine the alternate propulsion system. So this definition itself says that so many factors are involved when we are going for a selection of a rocket propulsion systems. So certain selection criteria are listed here, which we will discuss in brief in upcoming slides. So mission definition, affordability, system performance, reliability, controllability, etc. So these are the selection criteria which one has to undertake when they are doing selection for rocket propulsion systems. So first we will see is mission definition. So the purpose, function and final objective of the mission of an overall system are well defined and their implications well understood. So what is the purpose of this rocket, what is its function and what is its final objective for the mission? So these all things has to be covered and has to be understood very well before going to the next step. So in this step, the payload, flight rhythm, vehicle launch environment and operating conditions are established. So when you are defining mission for a particular application, then you have to undertake these basic variables, that is payload, flight rhythm, vehicle launch environment and operating conditions for that particular kind of mission. Then it is affordability. So the estimated life cycle costs are acceptable. They are the sum of the R&D cost, production cost, facility costs, operating costs, and decommissioning costs from inception to the retirement of the system. So one has to consider all the costs available, which will include the cost from the R&D to the retirement of the system, and it should be affordable for the person who is about to select the rocket propulsion system. Then the next factor is the system performance. So the propulsion system is designed to optimize vehicle and system performance using the most appropriate and proven technology. Inert mass is reduced to a practical minimum using improved materials and better understanding of loads and stresses. Residual or the unused propellant is minimal. So the rocket propulsion system which we have to select, so the system performance for such system has to be optimized using different proven technologies and most appropriate materials. So one has to take care that there is no negligence in system performance while selecting a rocket propulsion system. Then the next one is survivability, that it has to be safe when we are selecting a rocket propulsion system. So all the hazards are well understood and known in detail. Even if failure occurs, the risk of personal injury, damage to equipment, facilities, or the environment should be minimal. Then the applicable safety standards must be obeyed. So one has to take care of all the risks which are involved when they are selecting a rocket propulsion system. And even if the failure occurs, the personal injury, damage to the equipment, facilities should be kept minimal. So one has to even take care of all such things as well. Moving on to the next factor, that is reliability. Certain likely failures occur, the system must shut down safely. Redundancy of key components should be provided where effective. High probability that all propulsion functions must be performed within the design tolerances. Functions of all the propulsion systems should be carried out into the desired tolerances, and if any failure starts to occur, then the system must shut down safely. So this kind of reliable the system has to be when we are selecting a rocket propulsion system. Then the next factor is the controllability. So controls need to be foolproof and should not inadvertently create a hazardous situation. Thrust vector control response must be satisfactory. Mixture ratio control must assure nearly simultaneous emptying of the fuel and oxidizer tanks. So the controls which we use to perform various operations, they should work 100% and there should be no hazardous conditions generated because of this control options. Then the next option, that is maintainability. So there must be easy access to all the components that need to be checked, inspected or replaced. Then trained maintenance personnel should be available. So the propulsion system which one has to select, so there must be very easy access to all the components that need to be checked, inspected or replaced. And the training maintenance personnel should also be trained in a very well manner such that none of the components are left unchecked. Then the next one is geometric constraints. That is, propulsion system fits into vehicle into available engine compartment volume, meets specified length or vehicle diameter. So this geometric constraints has to be taken care of when we are selecting a rocket propulsion system. Then the next factor, that is prior related experience. So the experience and validated computer simulation programs are available and experimental skilled personnel are also available. Successful flight history is present. So all this experience has to be explored and studied very well before selecting a rocket propulsion system. Moving on to the next factors, that is operability. So the system should be simple to operate and validated operating manuals should exist. Procedures for loading propellants, arming the power supply, launching, igniter checkout, and so on must be simple. So the major tasks which has to be performed in a rocket propulsion system, these all controls should be easy and one should understand them carefully while selecting a rocket propulsion system. Next one, that is producibility. So it has to be easy to manufacture, inspect and assemble. All key manufacturing processes are well proven and understood. So the rocket propulsion system which one has to select, so it should be easy to manufacture and all the manufacturing processes should be understood very well, which will help to inspect and assemble in case of any emergencies. Then the next factor, that is schedule. So the overall mission can be accomplished on a time schedule that allows the system benefits to be realized. R&D, qualification, flight testing, and or initial operating capability are completed on a pre-planned schedule. No unforeseen delays has to be made. So when we are selecting a rocket propulsion system, the schedule which we have for our mission, it has to be completed within the specified duration. So this is one of the factors. Then the next factor is environmental acceptability. No acceptable damage to personal equipment or the surrounding countryside. No toxic species in the exhaust plume. Noise in communities close to a test or launch site should remain within tolerable levels. So the propulsion system should include all the factors which we have discussed earlier, with the factor that it should be environmental friendly and should not damage the environment. Then the last factor is reusability. So some applications, example shuttle main engine, shuttle solid rocket booster, or aircraft rocket assisted attitude boost, requires a reusable propulsion system. So if we are dealing with such kind of problem definition, so even reusability has to be understood and measures has to be taken when selecting the rocket propulsion system. So next it comes to the interfaces. So the interfaces assure system functionality and compatibility between the propulsion system and the vehicle with its other subsystems under all likely operating conditions and mission options. So the compatibility between the systems, that is the propulsion system, the structural system, all has to be maintained, but there are some of the interfaces which we will discuss now. So first one is the structural interface. So the interface for mounting propulsion systems has to be understood. Then restraints on masses, moment of inertia, or the location of the center of gravity, type and degree of damping to minimize the vibrations. So these are the structural interfaces which has to be understood, and some compromise has to be made to meet the compatibility between the propulsion system and the vehicle with its other subsystems under all likely operating conditions and mission options. Then under the mechanical category, there are interfaces for electric connectors, for pneumatics, hydraulics, propellant pipe connections. Then volume space for propulsion system is available and no geometric interference with other subsystems. So already a defined volume or space has been given for the propulsion system, so no other geometric interference has to be made with other subsystems. Then access for assembly, part replacement, inspection, maintenance, repair has to be taken care of. So in the category of power, there are other detailed interferences like source and availability of power, usually electric, but sometimes hydraulic or pneumatic, and their connection interfaces has to be understood. Identification of all users of powers, that is solenoids, instruments, TVC is thrust vector controlling, igniters, sensors, and their duty cycles. Power distribution to the various users has to be understood and identified while checking for the compatibility. Then the next set of interferences is the propellants. So sharing of propellants between two or more propulsion systems is important. Then vehicle flight controls and communication. So the command signals, that is start, stop, throttle, etc. and interference correction. Then under thermal, heat from the rocket gas, exhaust plume, hot walls of propulsion system components, or aerodynamic airflow should not overheat critical exposed adjacent components. So thermal interface, structural interface, and mechanical interfaces mostly include such kind of options which has to be taken care of. Then under plume we have impingement, control nozzle with vehicle components. Then lastly the safety, that is condition monitoring and sensing of potential imminent failures and automatic remedial actions to prevent or remedy impending failure has to be understood. For example, reduce thrust or shut off one of several redundant propulsion systems should be carried out safe and has to be compatible with other interfaces present. So this covers the selection of rocket propulsion system and the interfaces present between propulsion system and the vehicle and its associated subsystems. Next we will move on to rocket testing. So, before rocket propulsion systems are put into operational use, they are subjected to several different types of tests, some of which are outlined below in the appropriate sequence in which they are normally performed. Now we will see different rocket tests which are performed one by one. So the first one is manufacturing inspection and fabrication tests. So once a a component or a product is fabricated, it has to be inspected for dimensional inspection, pressure tests, X-rays, leak checks, electric continuity, electromechanical checks, etc. So these tests are carried out on individual parts which are fabricated. Then the next test which is carried out is component tests, which is performed on functional and operational tests on igniters, nozzles, insulation, valves, thrusters, controls, injectors, structures, etc. So under this tests, all these components they are checked for their functional and operation. If they perform up to date as desired, then the next test is static rocket propulsion system tests, which is with complete propulsion system on a test stand. So test stand is present on which the complete propulsion system is mounted and the tests are carried out. So under which we have A and B category. So under A category, the complete propulsion system tests are carried out which has underrated conditions, off design conditions with intentional variations in environment and calibration. Then under B category we have with liquid propellants or partial or simulated rocket operation in which for proper function, calibration, ignition, operation often without establishing a full thrust or operating for the full duration. This kind of test is performed. So for a reusable or restartable rocket propulsion systems, this can include many starts, long duration endurance tests, and post-operational inspections and reconditioning. So under static rocket propulsion system test, these two categories are present, in which first one it will use off-design conditions with intentional variations in environment or calibration. So some variations will be made to check some of the conditions, then underrated conditions are used. While as in B category, liquid propellants are used, which may include many starts, long duration endurance tests, and post-operational inspections and reconditioning. Then the fourth test which is carried out is static vehicle test, in which rocket propulsion system is installed in a restrained non-flying vehicle or stage on vehicle static test stand. So in the third test we have seen that a propulsion system is inspected or checked. In the fourth step, this propulsion system is installed on a restrained or a non-flying vehicle or a stage and checked for its various performances. Then the last test is the flight test. So once all these four tests are approved and nothing has to be corrected, the last step it comes to the flight test. Again under which we have two categories, that is A and B. So under A, with a specifically instrumented or new propulsion system in the development flight test vehicle, this flight test can be carried out for a new propulsion system in a development flight test vehicle, or it can be used for a production vehicle as well. So these five tests are the important tests which are carried out for any rocket which has manufactured and is about to go for a mission. Then each of these five types of tests can be performed on at least three basic types of programs. So we can use these five types of tests on some programs. That is, first one is research on and development or improvement of a new rocket engine or rocket motor, their propellants, materials or components. So it can be used for a research purpose for the development or improvement of a rocket engine for their propellants, their materials or components. Then evaluation of the suitability of a new rocket engine or novel rocket motor for specified application or for flight readiness. Even it can be used for evaluation of suitability of a new or modified rocket engine for its specified application. Then production and quality assurance of a rocket propulsion system. So these are the three categories for which the flight testings can be used. Next, we will see some of the factors or some of the physical quantities measured in rocket propulsion test. So the quantities which are measured are the first one, that is forces. So various forces like thrust, thrust vector, control side forces, short thrust pulses. So these all forces are calculated in the rocket testing. Then the flows, hot and cold gases, liquid fuel, liquid oxidizer, leakage. These flows are checked. Then the pressure, chamber pressure, propellant pressure, pump pressure, tank pressure, etc. are measured. Temperature of the chamber or the case, then wall temperatures, propellant temperatures, structure temperatures, and the temperature at the nozzle are calculated. Timing and command sequencing of the valves, switches, igniters, and so on is also checked. Sixth one is stresses, strains, and vibrations in combustion chamber, solid propellants, liquid propellant lines are also checked. The next set of quantities are time sequence of events, that is ignition, attainments of full pressure, that is ignition, attainment of full pressure, So the time sequence in between these processes are calculated, then the movement and position of parts, valves, stems, gimbal positions, deflection of parts under load or heat are measured and inspected, then the voltages, frequencies and currents in electrical or control subsystems are measured. Then visual observations are carried out for flame configuration, test article failures, explosion using high-speed cameras or video cameras. So even visual observations are carried out during these rocket testings using high-speed cameras or video cameras. Then the last one is special quantities such as turbopump, shaft speed, liquid levels in propellant tanks, burning rates, flame luminosity or exhaust gas composition, etc. are also measured or quantified during the rocket test. So the summary for today's class, we have covered the entire vast domain of rocket propulsion and its various factors. The first, we have seen a brief history of rocket propulsion engines. It started with the Chinese, then the Russian involved, then the Germans were involved, and Americans also played a vital role in discovering this rocket propulsion engines. Then we have seen the fundamental background about rocket propulsion, where we saw how Newton's third law of motion is the operating law for rocket propulsion systems. Then we have seen difference between an air-breathing and rocket engines and various applications of rocket engines such as space launch vehicles, spacecraft, missiles, etc. Then we have seen wide classification of rocket propulsion engines, in which we saw first that is chemical, in which it included solid, liquid, gaseous and hybrid based on their physical states. Then we have seen nuclear rocket engines, which has nuclear fission and nuclear fusion. Then under electric we have seen electrostatic, electromagnetic and electrothermal rockets. So for classification we have seen some important definitions regarding rocket propulsion, which included thrust force, specific impulse, thrust to weight ratio, combustion efficiency, mass ratio, burning time, etc. Then we have covered various selection criteria for rocket propulsion engines, which were mainly the mission definition, affordability, survivability, reliability, operability, etc. Then we have seen different kinds of rocket testings for rocket propulsion engines, which included manufacturing test, component test, static rocket test, static vehicle test, flight tests, and etc. Also, we have seen that how these tests are used for three different programs, that is for research or for evaluation of a new rocket or a modified rocket or for the production tests for rocket engines. Then we have seen various physical quantities which are measured in rocket propulsion testings, which included forces, flows, pressures, temperatures, stresses, etc. So this covers the fundamentals of rocket propulsion, and the references for today's class are present here. In next class, we will start with liquid propellant rocket engines. Thank you.